Hello, everyone. Welcome to Live Coding a Machine Learning Model from Scratch. My name is Sara Robinson. I'm a developer advocate on the cloud platform team focused on machine learning. You can find me on Twitter at srobtweets, and most recently, you can find my blog at sararobinson.dev. So let's dive right in with what we're going to cover today. I'm going to start out with a quick overview of what machine learning is. Then I'll talk about the model we'll be building. And finally, we'll get to the live coding. So at a high level, what is machine learning? I really like this definition, using data to answer questions. The idea here is that as we provide more and more data to our machine learning systems, they'll be able to improve and generalize on examples that they haven't seen before. So we can think of almost any supervised learning problem in this way. We have our labeled training inputs. We feed them into our model, and our model outputs a prediction. Now, these training inputs could really be anything. It could be the text of a movie review, and our model could be doing sentiment analysis to tell us that this is a positive review. It could be numerical or categorical fitness data, and maybe our model predicts the quality of the sleep that we'll get. It could be image data. So in this example, our model is predicting that this is an image of a cat. So this model concept can seem really magical, but it's actually not magic. Under the hood, it all boils down to matrix multiplication. So if any of you remember y equals mx plus b from your algebra classes, this might look familiar. So the idea here is that you have your features as matrices, those are your inputs, and then you have the thing you're trying to predict. And then you have these weight and bias matrices. And when these are initialized, they're initialized to random values. So the idea here is that as you train your model, you'll find the optimal values for these weight and bias matrices so that you get high accuracy predictions. So that sounds great, but you might be thinking the examples I showed on the previous slides, none of those had matrices anywhere. Well, it turns out that you can represent pretty much any type of data as a matrix. So this image, as an example, all an image really is just a bunch of pixels. And this is a color image, so each pixel has a red, green, and blue value, or an RGB value. So this image becomes 3 matrices of the RGB values for each pixel. Let's say you have categorical data. So for a particular column in your data set, it describes the industry that a person works in, and there's 3 possible values. The way you encode categorical data is through what's called one-hot encoding. So to do this, we create an array with the number of elements corresponding to the number of categories you have, in this case 3. And all of the values are 0 except for a single 1. And the index of that 1 corresponds with the value of that category. So maybe you're thinking, wouldn't it be easier if we just numerically encoded these healthcare 1, finance 2, retail 3? We could do that. But then our model would interpret these as continuous numerical values. So it would assign higher weight to retail. I would say retail is greater than finance, which is greater than healthcare. And we want our model to treat all these inputs equally, which is why we one-hot encode them. So I've shown you how we can transform our data for our machine learning models. In this talk, I want to share with you some tools on Google Cloud that can help you build ML models. And I like to visualize this as a pyramid, where you can choose your level of abstraction. If you want to get down to the details of matrix multiplication and building all the layers for your model from scratch, which we're going to do today, you can do that. But you also don't need ML expertise to get started. So the tools on the bottom of the pyramid are targeted more towards data scientists and ML engineers. And as we move towards the top, these are targeted towards application developers that may not have machine learning expertise. So in this talk, we're going to be building a model with TensorFlow, and we're going to deploy it on Cloud AI platform. The idea here is to turn you all into data scientists and ML engineers. So when I was thinking about the type of model I wanted to build for this, I wanted to choose something that would resonate with developers. And as a developer, there's one tool I can think of that I use on a daily basis, and that is Stack Overflow. So I wanted to build a text classification model to see if we could predict the tags of a Stack Overflow question. To do this, we need a lot of data. And luckily, we have a public data set available in Google Cloud BigQuery, which is our big data analytics warehouse on Google Cloud Platform. BigQuery has lots of really interesting public data sets for you to explore and play with. And they happen to have one of Stack Overflow questions. And it doesn't have just a few Stack Overflow questions. It has over 26 gigabytes and over 17 million rows of questions. So this is a great place to get started. Since we don't have a ton of time, I wanted to simplify the problem space. So in this example, we're just going to be classifying questions that have these 5 tags related to data science and machine learning. So for this particular question, our model should categorize it as Pandas, which is a Python library for data science. So our first step is to get the data from BigQuery. BigQuery has a great web UI where we can write SQL directly in the browser, get our data, and then download it as a CSV, which is what I did. So I'm extracting the title and the body of the question, concatenating them into one field, getting a comma-separated string of the tags, and then we're only getting tags with these questions with these 5 tags. So I ran this query, and as I was looking at the results, I noticed something. A lot of the questions, the question posters, conveniently, will put the name of whatever framework they're using in the question, which is very helpful. But that got me thinking, do we actually need machine learning for this? Could we just replace our entire ML system with an if statement? If TensorFlow is in the question, tag equals TensorFlow. The answer is no, because although lots of question posters do this, there are a lot of people that post questions that are really good questions, but they just dive right into the code, and they may not mention the framework or tag name. So we want to capture these questions too. And we don't want our model to just pick up on those signal words so that it only identifies questions with the word TensorFlow in them as TensorFlow. We want it to be able to generalize to find patterns among these tags. So when I was pre-processing the training data, what I wanted to do was take out these obvious keywords. So I thought I could replace them with a common word. And because everybody loves avocados, I replaced all of these words, including abbreviations for the frameworks, with the word avocado. So the result in BigQuery looks something like this. We have our questions. We have avocado predictive models. We have avocado data sets. Lots of avocados everywhere. So what I didn't talk about before was how we encode free-form text data into matrices. There's a couple different approaches for doing this. I'm going to use one called bag of words. This is a really simple one for getting started. So you can think of each input to your model in bag of words as a bag of Scrabble tiles, whereas instead of a letter on each tile, you have a word on each tile. So this type of model cannot detect the order of words in a sentence, but it can detect the presence or absence of certain words. So to show you how this works, I want to show you a really simple example. So for this example, we'll limit our problem space even further to say we're only tagging questions with 3 types of tags. And bag of word models have a concept called vocabulary. So pretend for a moment that you're learning English for the first time, and you only know these 10 words. That's how our model is going to look at the problem. Might lead to some interesting conversations. But pretend we only know these 10 words. So when we take this input question, how to plot data frame bar graph, we'll look at our vocabulary and we'll say, OK, I recognize these 3 words. The rest of the words in the question are going to be gibberish to the model. And when we feed all of our questions into our model, we want to feed them in as matrices that are the same size. So what we do is our question becomes an array the size of our vocabulary, with 1s and 0s indicating which words from our vocabulary are present. So because data frame is the first index in our vocabulary, the first element of our array becomes a 1, even though data frame is not the first word in our question. Same goes for graph and plot. So to summarize, our question becomes a vocabulary-sized array of 1s and 0s. It's called multi-hot encoding. And our prediction, since for this particular model, our model is going to be able to identify a question that has multiple tags, not just one. So this will also be a multi-hot array. So now we know how to encode our text data for our model. And what does our model actually look like? So the input data to our model is going to be that vocabulary-sized bag of words matrix. And then we feed that into what's called hidden layers. So this is going to be a deep neural network, which means that we have layers in between our input and our output layer. So it's going to take this vocabulary-sized array and resize it to whatever size we choose for our second layer and our third layer. Now, the output of these hidden layers doesn't mean too much to us. Our model's using it to represent complex relationships. But what we really care about is the output of our final layer. There's many options for how you can compute the output of this layer. We're going to choose one called sigmoid. And what this will do is it will return a value between 0 and 1 for each tag, which corresponds to the probability that that tag is associated with this question. So for this particular example, it looks like the question has a high probability of being about Keras or TensorFlow. So what are all the tools we're going to use to build this? I already showed you how we use BigQuery to gather our data and downloaded the CSV. We're going to use 3 open source frameworks to do some pre-processing and some transformations on our data to get it into the right format. We'll use Pandas, scikit-learn, and Keras. We'll use TensorFlow to build our model, specifically tf.keras. We will run our training and evaluation in Colab. Colab is a Python notebook that's cloud-hosted, and you can run it in the browser. It's totally free for anyone to use. And finally, we'll deploy our model on Cloud AI platform. So the title says live coding. Let's go over to the demo. Can we switch to the demo? Awesome. OK, so here we have our Colab notebook. It's connected. Again, anybody can access Colab in the browser, colab.research.google.com. And as you can see, we've got no code in here. What could go wrong? Just a bunch of comments. So I'm going to start writing some code and run these cell by cell. So what I'm going to use is Colab has this handy snippets tool. So I've saved a couple of the snippets for this notebook that I'm just going to drop in here. So the first one is, we are going to run this anyway. All right, had to reset the runtime. And now we are connected. So our first cell is just importing all of the libraries we're going to use. We're using TensorFlow, Pandas, NumPy, a couple of scikit-learn utility functions, and then we're using Keras to build our model. So we've got all of our imports. Let me actually make that just a tad bigger so that you can all see. The next thing we want to do is authenticate. Here we go. So Colab also has a handy authentication function that we can run. And what this will do is we'll pop up a URL for us to authenticate to our cloud account. So I will allow access, copy this code, and paste it in. OK, so now we are authenticated. And now we're going to get to the fun stuff. So first, we want to download our CSV. So now that I'm authenticated, I have saved all of this data in a CSV in Google Cloud Storage. That's our object storage tool on Google Cloud Platform. So I'm going to download the CSV to my local Colab instance. And then what I'm going to do is I'm going to use Pandas to read this CSV in. So let me just read it in here. And this will transform our data into what's called a Pandas data frame, which you'll see in a moment. The next thing we're going to do is we're going to shuffle our data. And this is a really important concept in machine learning. In case your data was in any sort of order before, you want to make sure that you shuffle it. And I'm using the scikit-learn shuffle function to do that. Data.head will let us preview our data. So this is what our data looks like. We've got our tags as comma-separated strings, and we've got our question text with lots of avocados. Now, we can't feed this in its current form to our model, so we're going to need to do some encoding. So first, we'll take care of the tags. So the first thing we want to do is encode these tags, as we saw in the slides, to multi-hot 5-element arrays, because we have 5 possible tags. So what I'm doing in the first line is I'm splitting each tag into an array of strings. And then I'm using this scikit-learn multi-label binarizer function, which will take all of those arrays of strings and transform them into a multi-hot array. So this is for the first question. We can see it's about TensorFlow and Keras. And here's this reference array that scikit-learn has created for us. So our input becomes this. So we've encoded our labels, and we are almost ready to move on to the questions. Before we do that, we need to split our data. So another important concept in machine learning is train, test, split. So we take most of our data, majority of our data, and we'll use it for training our model. In this case, we'll do 80%. We set aside a smaller portion of our data to use for testing so that we can see how our model performs on data that it has never seen before. So in this case, we have 150,000 questions in our training set and 37,000 in our test set. So we will now split our labels into training and test sets. And we'll say test tags equals tags encoded. We'll run that. So we've got our labels ready to go. And the next thing we want to do, so our label data is ready to go. Now we need to encode our question data into bag of words matrices. So I've written a class to do this. I'll paste that in here. It looks like a lot going on, but I'll explain. So what's happening here is we're using this Keras Tokenizer utility. So luckily, we don't have to do all that code of converting our freeform text to bag of words by hand. Keras has this utility that'll do it for us. All we do is pass it our vocabulary size. So in the super simple example that I showed before, we had a vocabulary size of 10. So that'll take the top 10 words from our data set. Since this data set is way bigger, I chose a vocab size of 400, which you'll see in a moment. So you want to choose something that's not so small that it only identifies common words across all of your questions. But you also don't want to choose something that's too big that your bag of words arrays become all ones. So we'll run this, and now we're actually going to use that class. So we will import it. And we will split our questions into train and test sets. So I'll do that. Right now, there's still strings. We haven't encoded them yet. OK, so the next step is to instantiate a vocab size variable, which is going to be 400. And now we will actually tokenize that text. So we're going to create a variable called processor and instantiate that text preprocessor class, passing it our vocab size. And now we can call processor.create tokenizer and pass it our train questions. That's this method right here. And then finally, the last part is actually creating those bag of words matrices. So this will be equal to processor.transform text, that method right there. And we'll pass that our train questions. And then the test set will be the same with our test questions, which we defined up here. So I'm going to run that. It's going to take a bit of time to run, because what it's doing is it's transforming all 180,000 of our questions from text to bag of words. So while that's running, we can keep writing the other cells, and they'll run when this one completes. So what I want to do is print the length of the first instance, should be 400. And then we're just going to log that bag of words matrix so that you can see it. And now we get to building our model. We'll come back to this when it finishes running. So the next thing that we want to do is save that tokenizer that we created, because we're going to need it when we deploy our model. We're using a Python utility called pickle to save that tokenizer object to a file. So now it's time to create our model. We've transformed our data. We've saved our tokenizer. Now we actually want to write the code to our model using Keras. I'm going to wrap this in a method. We'll call it create model. And it'll take our vocabulary size and our number of tags. And we're going to use the Keras sequential model API to do that, which I imported above. This is my favorite API for building models, because it essentially lets you define your models as a stack of layers. So you'll see that the code we're about to write will correspond really nicely to that model diagram that I just showed. OK, so it looks like this cell finished running. So we can see that this is what the first bag of words input looks like for our first question. It's an array of ones and zeros. So let's continue building our model. So the first layer to our model is going to be a dense, fully connected layer. That just means that every neuron in the input layer is connected to every neuron in the output layer. We need to tell our first layer what the input shape is going to be. In this case, it'll be the input of our vocab size, which is 400. And then finally, we need to tell Keras how to compute the output of this layer. The great thing about Keras is we don't need to know exactly how this activation function works under the hood. We just need to know the correct activation function to use. So in this case, ReLU is what we'll be using. We'll add one more hidden layer, also with the ReLU activation function. We don't need input shape here, because it'll infer it from that previous layer. So far, these are our hidden layers. So we don't care too much about the output of those layers. But what we do care about is the output of our final layer. And that layer is going to have 5 neurons. It'll be a 5-element array, since we have 5 tags in our data set. And the activation function here will be sigmoid. So that's really all the code for our model, just 4 lines of code. We've defined our model in Keras. We need to run model.compile so that we can actually train and evaluate this model. And to do this, we need to tell it a couple of things. So we need to tell it our loss function. This is how Keras will compute the error of our model. So every time it runs training, it'll use this function to say, OK, what was the error between what the model predicted and the ground truth, what it should have predicted? Again, we don't need to know exactly how this particular loss function works under the hood. This is just the best one to use for this type of model. I also need to tell it my optimizer. The optimizer is how the model will update the weights after it goes through a set of data. And then finally, I want to tell it how to evaluate my model as it's training. And we're going to use accuracy as a metric here. So I will return my model. And now we'll actually create our model. So we'll call create model. We'll pass it our vocab size and our num tags. And then we can use this model.summary method to see what our model looks like layer by layer. So we can run that. We've got our model ready to go. We have not trained it yet. So the next thing we'll do is we'll train our model. And we can do that with one method call, just model.fit. We pass it a couple of things. We pass it our bag of words array. That's our input, our features. We pass it our labels. Those are the tags, which we've encoded. We need to tell it how many epochs to run training for. What this means is that this is how many times our model will iterate over our entire data set. So we'll go through our entire data set 3 times. Batch size is how many elements our model will look at one time before it updates the weights. In this case, we'll use 128. And then I'm going to pass an optional parameter called validation split, which will take 10% of our training data and evaluate it as our model is training. So we're going to run training, and it should train pretty fast. And what we ideally see here is that our validation and our training loss is decreasing. So that's a good sign. We've got our validation and training loss decreasing. If your validation loss is increasing as your training loss is decreasing, it might be a sign that your model is learning the training data too closely. We can see that our accuracy is 96%, which is pretty good. So next step is evaluating our model. So that 20% of the questions that we set aside, we're now going to see how our model performs on that data. So we call model.evaluate. We pass it our test bag of words, our test tags, and we tell it our batch size. And our evaluation accuracy is very close to our training accuracy, which is a good sign. And then the last thing we want to do is save our model to a file. Keras uses the H5 file format. So we'll save our model. And now we're going to test it out locally. So we have a custom prediction class that I've written. And all this is going to do is pre-process our data. So it'll instantiate our model, our saved model from the file. It'll instantiate our tokenizer. It'll take the question as text, transform it, and then return a prediction, that sigmoid probability array. So let's save some questions to predict. This is just an array of 2 sample questions. And then we will make a prediction on our local model. So this should return, cool. So for the first question, it predicted Keras, which was accurate. The second one predicted Pandas. So we've got our model working locally. Accuracy is 96%. Next thing we want to do is package and deploy it to AI platform. So I've written some code to do this. And one of the features that we're going to make use of that's new to Cloud AI Platform is custom code, which lets us write custom server-side Python code that's run at prediction time. Now, this is really useful because it'll let us keep our client super simple. So our client will just pass the text to our model. We don't want to have to do any transformations on the client. We'll pass our text to the model, and on the server, we'll transform that text to bag of words and then return the correct tags. So to do this, we'll need to copy some files to Google Cloud Storage so that Cloud AI Platform can find our model and our tokenizer. I'm going to use the Google Cloud CLI gcloud to set my current project to the one I've configured for this demo. And finally, we want to deploy this to AI Platform. So here's the deploy command that we're going to run. We're going to set our minimum nodes to 1 so that our model doesn't scale to 0. And I'm going to create a new version called O'19. And we are going to deploy that. That'll take a couple of minutes to run. But if I look over here in the Cloud AI Platform model UI, we can see that my model is deploying, which is pretty cool. So while that's deploying, let's go back to the slides. So we built something that looks pretty good. We've written some code to pre-process our data. We've trained a model with pretty high accuracy. But can we do better? Right now, our model is pretty much a black box. We don't know how it's making predictions. We know that the predictions are accurate, but we don't know what's making it make those conclusions. So as Sundar mentioned in the keynote, we want to make sure that our model is using data to make predictions in a way that's fair to all of our model users. To do that, we need to uncover the black box. And as model builders, we need to remember that we're responsible for the predictions generated by our model. This may sound really obvious, but we need to take steps to avoid bias by making sure that our training data is representative of the people that are using our model. Luckily, there's a lot of great tools to help you do this. I'm going to look at one open source tool called SHAP. And what SHAP will let us do is interpret the output of any machine learning model. So we'll use it here for our tf.keras model, but we could use it for any type of model. The way SHAP works is we'll create what's called an explainer object, passing in our model and a subset of our training data. And then SHAP returns these attribution values. So what the attribution values are is it's positive and negative values indicating how much a particular feature impacted our model's prediction. So let's say we had a model with 3 features. We'd get back a 3-element array of attribution values. High positive values mean that that particular feature pushed our prediction up. Negative values would mean it pushed our prediction down. Well, how will this work for our bag of words model? So what I configured SHAP to do was I had it treat that 400-element vocabulary array as 400 features. And so we get back 400 different attribution scores. And we can take the highest values from that and the lowest values to see which words had the most impact on our model. So I wrote a little code to do this. I don't know if the colors are showing up well in there. But what this is I took the top 5 highest and lowest attribution scores so that I could see which words our model was using to make predictions. So this particular question is about pandas. And it picked up on the words column, data frame, df, series, which is good, because those are all words that are specific to pandas. Words that contributed least were for, each, and you, which are fairly common words that you might find in any Stack Overflow question. So this is a good sign that our model is working correctly. So let's go back to the demo and take a look at SHAP. So it looks like our model finished deploying. I'm going to go ahead and set that as the default version. And before we get into SHAP, we will generate some predictions on our deployed model. So I'm going to write a file with some test predictions. And now we're going to use the Google Cloud CLI to get some predictions on our trained model. So we call gcloud AI platform predict. We pass it our model name, which is Stacko model. And we pass it our text instances, which is this predictions.txt file that we just saved. And we will run that. And now we are going to print our deployed model predictions. So it looks good. Our model, we're calling our model that's deployed on AI platform, and it has predicted Keras successfully for the first question and Pandas for the second question. So now let's use SHAP to explain our model. So SHAP does not come pre-installed in Colab, so we will install it via pip, and then we will also install this module called colored, which I use to color the text, different words of the text. So once that's done installing, we will import SHAP, and we can create our explainer. So we will create what's called a deep explainer. SHAP has many different types of explainers. We're going to use the deep explainer, and we're going to pass it a subset of our training data. And then we will create our array of attribution values. So we can call explainer.SHAP_values, and we pass it a subset of our test data. In this case, we'll just take the first 25 examples from our test set. So we've got our attribution values. The next thing we want to do is print them in a nice way. So first, to do that, we're going to take that tokenizer that we created in Keras, which is a dictionary, and we're going to convert it to an array so that we can take our attribution values from SHAP and see which word they correspond to. So we'll convert our tokenizer to a word list. And here we can see the top most frequently occurring words that our model vocabulary is using. And the first thing we want to do is print a summary plot, which is a method we have in SHAP, to see a summary of the words that are most impactful on our model's predictions. So we'll pass it our SHAP values. We'll also need to pass it our feature names, which is that word list we just created, and along with our class names, which goes all the way back to our tag encoder. So if I wrote that correctly, we should get this nice plot here. And what this tells us is the highest magnitude words that our model was looking at. So it looks like data frame was the word that our model used most to make predictions, probably because there was the most Pandas questions in our model. And we can see that data frame was most impactful for Pandas. It was also a signal word for the other libraries, probably a negative signal word. And then we can see the other words that were impactful here. So plot was most important in matplotlib predictions, which makes sense. And we can see all these other words down the list. So that gives us a nice aggregate view of how our model is making predictions for this particular data set. And now, if we want to highlight individual words, I've written some code to do that so that we can see for a particular question which words are signaling predictions. So here's an example of a Pandas question. The words column. A lot of Pandas data frames have columns that have not a number of values. And then we see common words like use and does are not being used by our model to make the predictions. For TensorFlow, we get it looking at words like session, sesh, ops, tensor. Here's a Keras example. Looks like the most common words are LSTM, layers, dense, etc. So now we can see how we can use SHAP to make sure that our model is behaving correctly. One way you might want to use this in a fairness example is if you have a model that's doing sentiment analysis, you want to make sure that it's using the right characteristics to predict positive and negative things in whatever type of text you're using. So if we could go back to the slides. To wrap things up, we're going to put this all together and get predictions from our model in a web app. So it would be really useful if we could, as we're typing a Stack Overflow question, see which tags are associated with it. So with the help of my teammate, Jennifer Person, you should follow her on Twitter, we built a Chrome extension. And what the Chrome extension does is it takes the HTML of our Stack Overflow question. It passes it to a Cloud function, which I've written using the Cloud function's Python runtime. The function will use the AI Platform API to make a prediction on our model. And then in our function, we'll return just the name of high confidence tags back to our Chrome extension. So let's see it in action. Oops. Let's go back to the demo. Here we go. OK, so here is an example question about matplotlib in pandas. I have just loaded up my Chrome extension locally. Looks like it's not working at the moment. Hold on one second. Live demos, you never know. Let's try it out once more. All right. Something's going on here. I'll try out the question draft. All right. Not working. But luckily, I have a video of what it was supposed to do. Sorry about that, everyone. Always have a backup. OK, so this is what it was supposed to do. Live demos, you never know. OK, so it's supposed to predict matplotlib and pandas for this question. And then we have a question that I've drafted based on the code that I wrote. And it predicted Keras for that one. I'm sorry that the demo didn't work. Let's give it one more shot. Yeah, OK, it looks like it's not working. Anyway, that's what the demo is supposed to do. If we could go back to the slides. So I covered a lot of different tools today. I just wanted to give a summary of everything we built. We built a custom text classification model using tf.keras. We deployed our model on Cloud AI Platform. I should also mention that I could have also deployed that SHAP code to AI Platform using the custom code feature. But in this case, I decided just to keep it super simple and do that part separately. We explained our model output using SHAP to make sure that our model was behaving in the way that we expected. And we kind of called AI Platform with Cloud functions. You saw a video of what it was supposed to do. These are links to all of the code that I showed today and all the different products. So the first link goes to a GitHub repo with the code for everything I showed. The other links are to various products that I covered. And finally, we are working on model interpretability support in Cloud AI Platform. So if you have a use case for it, if you want to stay in the loop and hear more about it, we'd love to hear from you. So please fill out this form at the bit.ly link at the bottom. And finally, please fill out the feedback on this talk in your I/O application. I really use that a lot to make the talk better the next time. So thanks, everyone.